So here's our equation for magnesium hydroxide dissolving, and we need to look at the concentration of the magnesium ion. So it's 0.025 molar. And we're looking for the concentration of hydroxide ion at which this precipitates. So we need to be a little bit careful here because this is two hydroxides coming from the magnesium hydroxide. So for a saturated solution, we've got the KSP is 2.06 times 10 to the minus 13. And that's going to be equal to the magnesium ion concentration times the hydroxide ion concentration squared. Well, this time we know what the magnesium ion concentration is, and so we're trying to find the hydroxide ion concentration. Yes?
So if we're adding potassium hydroxide, why do you write the magnesium hydroxide first if the reactants are going to be the magnesium ions in solution and the hydroxide ions added to solution?
Well, we're looking at magnesium hydroxide because that's the precipitate that's going to form.
So it doesn't matter which side you write it on?
The KSP is set up for the equation to be written this way, with the solid on the left and the soluble ions on the right. If we want to write it the other way around, then we have to use the reciprocal of KSP. So it's just easier to do it this way. So if I want to know what the hydroxide ion concentration is, it's going to be the square root of the KSP divided by the concentration of the magnesium. Anybody else get that number?
Yeah.
Okay. Phew. Did something right. Well, we'll see. 2.9616.
So for this one, we're only worried about the magnesium hydroxide because that's the one that will cause it to precipitate first.
Yeah, what we're looking at, of these two ions, magnesium and calcium, magnesium hydroxide is less soluble than calcium hydroxide. So as we add hydroxide, the magnesium will precipitate first. And so that's what we're going to look at. At what hydroxide ion concentration will we start to see magnesium hydroxide precipitating? And it's here, this is a saturated solution. You go past that and you'll begin to get precipitate.
Just curious if this is like theoretical numbers, or is it possible to get down to that concentration?
Sure, you can get down to that concentration.
And have it that precise?
Well, have it that precise? I don't know. But I mean, this concentration of hydroxide, is a pH of 8.46.
I was just wondering how accessible these instruments would be to create these. Like, is that why science is so expensive?
Well, so this sort of thing is more of a wet chemistry technique, which is not used for quantitative analysis anymore. It's sometimes used for qualitative analysis, and in fact, that's what your lab practical is going to be. It's a series of selective precipitations to find out what ions are in your mystery solution. It's not great for just general quantitative calculations. For those of you that did the calcium oxalate precipitation in 1A where we use the little Gooch crucibles, that's the idea here. But there we're not doing a selective precipitation. We're trying to quantitatively precipitate all of the ion of interest, and we do that by adding an excess of the precipitating agent. So if we had the solution of magnesium at 0.025 molar, and we wanted to analyze how much magnesium was in there, we'd add a whole ton of extra hydroxide to make sure that we get all of it precipitated.
What about the calcium?
Well, then the calcium would precipitate too, and so that wouldn't work. But we can separate them and get a pretty good separation. Yeah. And all of these numbers, KSPs here have 3 sig figs. A lot of the KAs had 2 sig figs. Now, could that be measured more precisely? Yes, but there are all these other factors like the exact temperature that are going to play into it as well, and so practically speaking, we can't use more sig figs. Oops. Okay, another question. So solution is 0.085 molar in lead 2 and 0.025 molar in silver. If selective precipitation is to be achieved using sodium chloride, what minimum concentration of sodium chloride do you need to begin the precipitation? To begin to precipitate the ion that precipitates first. That's a tongue twister. And then what is the concentration of each ion left in solution at the point where the second ion begins to precipitate? So we've got 2 problems here. So the first question is, which ion is going to precipitate first? The silver chloride, because it has a smaller KSP. So the first question, minimum concentration of sodium chloride needed to begin precipitating the silver ion. So silver chloride in equilibrium with silver and chloride. And we got KSP right there. So we have a solution that's 0.025 molar in silver. And we want to know what the chloride ion concentration will be when that begins to precipitate. So KSP is silver ion times chloride ion. And so we're trying to find the chloride ion, so we could just rearrange this equation first. The chloride ion concentration is going to be equal to KSP divided by the silver ion concentration. So KSP is 1.77 times 10 to the minus 10. And silver ion is 0.025. We need 7.1 times 10 to the minus 9. So your calculator is showing you 0.000000007. Put it in scientific notation. There's more digits. Press mode up at the top. It'll give you a menu. On the second line, norm, sci, eng. Hit sci and enter and then quit, and enter again. Okay, so that's part A. Part B, what concentration of each ion is left in the solution at the point where the second ion begins to precipitate? So the second ion is the lead. So the lead is going to precipitate. And I think it's really helpful to write out the equation here to make sure that you're using the correct KSP expression. So the lead concentration is 0.085 molar. KSP for this is equal to the lead times the chloride ion concentration squared. And so the chloride ion concentration here is going to equal to the square root of KSP divided by the lead concentration. KSP is 1.17 times 10 to the minus 5. Our lead concentration is 0.085. We're taking the square root of that. I'm getting 1.17 times 10 to the minus 2. Anybody else get that? I got it twice. Okay. So as we're adding chloride, when we get to this concentration of chloride, the lead will begin to precipitate. And so it's asking, what concentration of each ion is left in solution? Well, what concentration of lead is in solution at this point? The lead ion concentration hasn't changed yet because we just got to precipitating it. So the lead concentration is going to be 0.085. What's the silver ion concentration? Is anything zero? No. It might be approximately zero.
Basically zero.
So the silver ion is going to be precipitating, right? And we're adding chloride. So if I've got, oops, not over there. If I've got 0.085 molar chloride and 0.025 molar silver, we could do basically a BA table. We could look at, well, the silver should precipitate 0.025 of this, yeah? That's an excellent question. I was testing you to see if you're paying attention. No, because I'm marginally functional for some reason today. Thank you. Yeah. So, yeah. We've added 1.17 times 10 to the minus 2 molar chloride ion. And we initially had 0.025 molar silver ion. I'm going to write this in unscientific notation because it's hard to look at that way. It's 0.0117. So is that much chloride going to precipitate all of the silver? It can't, because we haven't added as much chloride as there is silver. Yeah. So there's going to be some silver ion left, right? So what we kind of need to do here is make an ice table. So if we start with this much of each and think about, well, what's the change going to be? This is going to go down by x, this is going to go down by x. And at equilibrium, I'm going to have 0.025 minus x and 0.0117 minus x, and I messed that up. So for the silver chloride, KSP is 1.77 times 10 to the minus 10. And that's going to equal 0.025 minus x and 0.0117 minus x. Now, you know, it's always tempting to use x as small, but if I use x as small here, what happens? I end up with 1.77 times 10 to the minus 10 is equal to 2.925 times 10 to the minus 4, which it's not. I'm going to try the solver here. And this may or may not work. I kind of think it might not, but I'm just going to throw caution to the wind and try it anyway.
Should we evacuate since we smell it?
What do you smell? Paint?
So we should evacuate. I don't want to get hot. I know, that's what I'm saying.
0.0116.
Yeah, so I'm getting x is 0.01169986.
This is crazy. Do you feel lightheaded?
No, I feel like the normal mess that I usually.
I feel, we felt that.
So x is actually very close to this 0.0117. Yeah.
I'm sorry, why did you plug in the 0.0117 for the additional?
Well, so this is how much chloride I've added to get to the point where the lead precipitates. None of the lead is precipitated yet, but I calculated this chloride concentration. When the chloride ion concentration gets to that point, it will precipitate the lead.